So my name is Abhishek. Thank you for the introduction. So this talk is going to be about the Q Challenge project, which is funded by BMW, and this consortium consists of different partners like ourselves, BASF, SAP, Siemens, BMW, and also a startup from Munich, coming out of LMU and LMU University as well. Now, what we're going to talk about is two use cases. One of them is a use case from BASF's business unit, which is we named it production assignment and scheduling. And the reason we did it, we named it so is because what we have in this problem is we are given certain number of jobs, we are given certain number of machines. It's not like in normal job shop machine, but here what we have is a job can be processed on several machines. So there is a list of eligible machines where a job can be processed. And each job has such a eligible list. The most important thing is that between any two jobs processed on any machine, we need to have this, what you see here, Sij or SKL, the setup time, to prepare the machine for the next job to be processed. So the red job, when it is done, we need to prepare the machine for the green job to be processed on M1. Now, processing the job is essential, meaning given as many jobs we have to finish all the jobs. So there is no time constraint. The time constraint is in reducing the setup times, the way we assign these jobs on the machines, and then we schedule them such that the total setup time is reduced. The objectives are threefold. One of them is to maximize the total value. The values are, by the way, given by these variables, VI1 and VJ1 and so on. Minimize the total setup times. This is one of the most important ones. And we also want to uniformly utilize all the machines, meaning it may happen that one machine is able to do all the jobs, and doing all the jobs on that machine will reduce the overall setup time. This is not desired. We would like to also uniformly distribute all those jobs on the machines. Uh, the solving methodology. So one thing I would like to say is any model, classical or quantum, is as good as its modeling, the mathematical model behind it. So what we did in this case was we did not blindly take a model and compare it on quantum as well as classical. We tried to formulate this problem the best we can on the quantum machine, and we try to formulate this problem the best we can on the classical machines. The best we can, the best of our ability is what I mean. So the quantum model, of course, is most useful, let's say, when all the variables are binary. So we try to model this problem using MTJ. Let's not go into detail, but the thing is, all the variables for the quantum model were all binary. Classical model enjoys actually if your problem has continuous variables or even integer variables. So here we try to model the problem differently and also have a different model so that we can use different LP algorithms like relaxations or cutting plane and so on, and then run the tests. So this is what we did. We had the model in the quantum way, we had the model in the classical way. We took the quantum model and ran it on the D-Wave CQM solver. I think Florian will talk a bit more about the CQM solver, but what I'm going to show are the results. So the plot on your left is showing, so we ran these problems ranging from 2,000 variables till 151,000 variables. Just to let you know, this is not a quantum computer, this is a hybrid quantum computer. It has classical as well as quantum hardware, as is said by D-Wave. The blue line tells me, so we gave D-Wave, depending on the total quota of runtime we had on D-Wave machines, we gave maximum of 1.5 hours of the runtime on all these problems on D-Wave, right? And then we get this blue line. Blue line is exactly this. So blue line is the runtime given for the D-Wave machine on all the problems, and we get certain result. The red line shows here how much time did Gurobi take to reach the same solution value what we obtained from D-Wave in the time given by this blue line. Yeah, and this we can see there is a bit more offset, or there is a bit more time required by the Gurobi solvers, and Gurobi solver is using all its the relaxation, the cutting plane methods, and everything. And the D-Wave solver is solving this binary model. And the right-hand side is basically the time required by the D-Wave machine divided by the time required by the time required by the Gurobi solver divided by the D-Wave machine. So basically how much speed up we have by the D-Wave machine or the D-Wave solver against the Gurobi. And this is ranging from, or let's say, from 1.5 to 2. So this was kind of encouraging because we haven't seen this before in any other use case. And albeit modeling the problems the best we can on the two different worlds. So, and I think we move on to the more prologue.
Yes.
Florian.
So I also presented the just seen use case last week at the Quantum Week in Montreal, and there's a preprint on archive, so you can see a more scientific approach to that and explanation of the two models. So the next use case we were working on, or we are still working on in our public funded project, is called Moprolog. It's a use case from another BMWK funded project. Yeah, and it's a production scheduling problem, including HEVs. HEVs are small autonomous cars bringing products from one machine to another or to the warehouse. And well, the objective is to minimize the make span or minimize the number of HEVs. And in this special use case, we have two products, product A and product B. Product A needs machine 1 first, then machine 2, and then it's finished. Product B goes machine 3, 2, 3, 2, and then it's finished. And you have to transport the goods to the machine, and you can then transport the goods from the machine 1 to 2, for example, or to the warehouse, and then from the warehouse to the machine. When we set up the optimization problem, a lot of things are certain. For example, we do not need the first machine 3. It only depends on the start of the second job on machine 2 for the product B. Product A, for example, machine 1 is quite deterministic, so we just need to decide which HEV to use from transporting it away from machine 1. The decision variables we have those 5 indices, and if this variable is 1, it tells you that this job J is brought or picked up from a certain machine M at time T. And the A gives you the HEV which is used, and D if it's picked up or brought to the machine. And the formulation we have is good for our hybrid solver because we can reformulate the linear constraint into quadratic constraints and have way less constraint. And currently the model we have, the linear model of that, is not very suited for Kurobi. So we are still thinking about a better way to model it. We're taking job scheduling approaches. We still need to verify if the two models are equivalent, so solving exactly the same problem. And yeah, doing the tests. Our preliminary results can seen here. And these are the same plots we had for the previous use case. So we let dwave run. It computes automatically the runtime it needs for that, and it produces some solution. And then we let Gurobi run and just took a look when it reached the objective value of dwave, and this would be on the left plot the runtime. And these are not the results we want to have, because here we compare the same formulation, or more or less the same formulation, for two different hardwares, whereas the formulation is not suited for Gurobi due to a huge number of constraints. And yeah, so in future work we will find a better model for Gurobi, and then probably have different plots. Let's see if the red line will be below the green line, so meaning Gurobi would outperform dwave in this situation. But this is still work in progress. Yeah, so what we saw that is dwave can give competitive results. For the past use case, I think we have two very reasonable models, meaning in these benchmarked, dwave outperformed Gurobi. For the second use case, we just saw it's for the same model, dwave is faster for a model which is not suited for Gurobi. However, we do not know how much quantum plays, or if quantum at all plays a role in the solution process. So taking it away, we could get better results maybe for dwave, and meaning it's just poor classical. Yeah, but the results are good. A second thing we basically knew before, but it shows again that this solution or the performance of a solver is only as good as the model you give it. So you can give the best model to D-Wave, the worst model for Gurobi, you will certainly get an advantage from D-Wave. But I mean, we do not want to solve certain formulations, we want to solve the problem itself faster. And a second thing is that we more or less only have a binary variables for quantum computing. If we use the CQM solver from D-Wave, you can also define continuous variables, but I don't know what happens to them in the background. And yeah, but we do not know any good methods for handling continuous variables in quantum computing. And also D-Wave doesn't tell us how they do it in the background. And yeah, thank you for listening.